So, if any of y'all had algebra yet, what's one of the main things you learn how to do in algebra? Reduce equations, right? And why? Easy to read, makes them less complex, right? Well, what we got to realize is that in Boolean algebra, some of the rules are different because there's no such thing as a squares or b squares. We have nothing raised to any power because all we have is ands and ors, right? What's that? No, no.
Okay. He
added to. Yeah. This class is an add to class.
Okay.
So we don't do anything that's null and void. We just add to. So we already talked about what's combinational logic.
Oh, you asked?
Yeah.
Oh, when you put more than one logic together.
To form a more complex task, right? So what's so neat is that everything that we're going to talk about this semester is going to be made from these 5 basic gates, but we're going to have to start moving into combinational logic. The first combinational logic gate we'll look at is something called an exclusive OR and exclusive NOR, which is the next chapter. Boolean algebra rules and laws, we'll look at that. But hopefully you'll see that most of this will make sense, especially if you understand the logic, right? And understand we don't have add and we don't have subtract. We have ands and ors, right? And then nots. Simplify combinational logic circuit using Boolean algebra. Now this is where this really becomes powerful, because in math, what you're doing when you reduce an equation in math, you're making it simpler. Well, and if I can take a circuit and I can come up with an equation for a circuit, and then I can reduce that, not only is it going to make the circuit simpler, but it's also going to save me money when I start building these things, right? So every gate that I can leave off would be money that I can save, or I can use somewhere else. We're going to look at something called De Morgan's theorem, even though we already know that. Basically, De Morgan's theorem says every and has an or function and every or has an and function. And that's where we come up with our negative and positive logic symbols. And we'll talk about what we can do with nands and nors. Nands and nors, we can make all the 5 basic gates out of nothing but nands and nors. So I can use a NAND and make an inverter out of it. I can use a NAND and make an OR gate, make it form as an OR gate using combinational logic. AND, ORs, inverter gates. Some of the products and this other stuff we're not going to get into. Karnaugh maps is another method of reducing equations. But what you do is you set up a matrix or rows and columns. And you take a truth table, so you have to come up with the truth table before you do the Karnaugh map. And truth tables can become very cumbersome, right? We're okay as long as we get up to like 4 inputs, but 4 inputs still has 16 combinations. So Karnaugh maps, what I would have to do is I'd have to develop a truth table for the circuit, and then I'd transpose that into a matrix of rows and columns, and then you would come up with a technique that you can reduce it. So I like to use Boolean algebra to reduce equations because you just do it once, right? That makes sense. So it's just another method of simplifying equations. So we already know this, right? Everybody okay here? Okay, this is just our, and we're going to add to this. I think, did I give you all the one with both the negative and the positive on there? Yeah. So right now we're working on the left-hand side, but by the time we get through here, we'll be over on the right-hand side. Combinational logic, we already know that. So I've got this circuit. First of all, being able to draw a circuit that represents the equation. So we'd say B, which is the output. It actually should be X, guys. So should be equal to what? K and D or H and D. So first thing we do to to draw the circuit is we look at the main divider. What divides the circuit up? Divides the equation up. And here we can see it's that OR symbol, right? Understand? So what that means is to draw the circuit that represents this circuit, I would start off with the main divider. So I'd come over here and draw an OR. And then I'd say, okay, this is an AND. So I'd come over here and draw an AND. And then I would put K, D. Then I'll come down here and draw another AND. And then put HD. So what I just did is I took an equation. If you're gonna reduce equation, the equation is not the circuit, right? You understand? So once you reduce the equation down, you're gonna have to figure out the equivalent circuit because that's what you're gonna build. That makes sense? Does it look like this will reduce? Well, what we're looking for is I'm looking for this. Now in math, if I saw two D's, I know that thing would reduce. So how would we reduce that? Well, I'd say B. Let's change this to X, guys, because that's the rest of the book teaches X. So first of all, I would say I would factor out the what? The D. So I'd bring the D out, and then I'd say K or H. Those two things are equal to each other. And that's exactly what you would have done in algebra.
Oh, I thought you were talking about as in.
Yeah, when you look at a Boolean equation, if you see a term used multiple times, it means that sucker is going to reduce.
No, I thought you were talking about actually drawing it out at circuit.
No, what I said, what it reduced.
Yeah, okay, I got you.
Right, that makes sense. So if I drew this circuit out, I'd say, okay, now I'm going to have my main divider between my two things is an AND, and then I would come over here, I'd bring a D straight in. And then I would come over here and put an OR gate. And then I would go what? K or H. And I would bring that in. Well, what we just did is we went from 1 to 3 gates to perform this logic to what? 2. Yeah, because that's this right here. So there's the OR. K or H, and D. Understand? Yeah, because that's the logic. That's the logic. We could do the truth table. So I could come over here and I could do the truth table. How many inputs do we have? Well, let's do the truth table here. Instead of me trying to draw the circuit, here's the actual circuit. So that means I come over here and I've got 3 inputs, right? 3, because 2 of them's got the same name. So my inputs would be equal to K, D, H. I'm going to have to move this up. K, D, H. And the output, they're calling it B because it's the buzzer, but let's call it X. And then I'll come over here and I'll just count, right? 0, 1, 2, 3, 4, 5, 6, 7. And then I'll come over here and I'll put zeros over here to start off with. What would be the output here? Output would be 0. This output would be 0. So this output would be what? 0. Are we okay? Now follow me so far. You okay, Brian?
Yeah. Now, I went back to the other day in our lab where we actually had 4 on each side.
Yeah, but that was 4 different. That was 4 different devices with the circuit, right?
Okay, so
that had 4 different outputs. This guy here's only got what? 1. So I'd come over here on the next one, and I would come over here, and I would put this truth table. So K is a 1, 0, D is a 0, H is a 1, and D is a 0. Okay, so the output of this would be a 0, this would be a 0. Everybody follow me so far? So this right here would be a 0. And what we're trying to do is prove the equivalent circuit as the same. And this basically is so when I get out of my car and I do any of these things, mine don't buzz. It goes ding, 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 indicating I've got out of the car, left my lights on, or stuff like that, right? Of course, not anymore, because most of your lights have an auto on it now. But so they automatically turn off. But in the old days, if you got out and you left your lights on, you wanted to know that, because what would happen? It'd run your battery down. So they came up with this technique that says, okay, if the ignition key is in there, mine does that. So if I open my door and my ignition key's in there, my car's not running, it dings that to let me know, hey guy, you're fixing to get out and do what? Lock your keys in your car. So this is saying, okay, if the ignition is on or the door is open, if the key's in ignition or the door is open, and I open the door, then the buzzer's going to sound. If the headlights are on and I open the door, then the buzzer's going to sound. So this is the way this circuit's going to work. This is pretty much, well, basically a circuit that's in your car, right? Of course, now it's probably not done by an individual circuit. Now it's probably done by a computer. Mercedes yesterday, Mercedes is setting up a automotive repair thing here on campus. So like, it's not going to be for technicians to fix things. It's going to be for automotive guys, under the hood guys. So we've already got Toyota. We got, good gracious, we got like 4 of them there already. So Mercedes is coming up there, huh? Yes. Well, just about they don't have any standalone, but every dealer has their own repair shop. Every dealer that I know of around, every new car dealer. Used car don't usually have that, but every new car dealer has their own. And that's who they train. So we do Chevrolet, I don't think we do Ford, we do Toyota, we do Chrysler, I think, Tom. So now we're doing Mercedes. So that was talking about, he said there's 34 computers in that car now. Huh? Yeah. So, cause he says, his car, it's not self-driving, but it'll change lanes for you. So if you're on the interstate and you put on your blinker, it'll do what? And it's got that thing on it too, where if you're in a traffic jam, you just sit back and tell it you're in a traffic jam. And every time the car in front of you moves, you move. So we're moving towards self-driving cars, guys. It's going to be in our lifetime. It's going to be in my lifetime. I'll probably never buy one. I'll be like Will Smith in I, Robot, or Sylvester Stallone in, what was that? No, he was one where he was the cop that got frozen and he came back, and Wesley Snipes was the bad guy. Yeah. What's the name of that movie? He liked to drive the car too. Self-driving car. Yeah, but that guy killed. They had a truck turn in front of him. It was in this lane, it turned, and it had a white body, and it was real cloudy, and the guy didn't, and the cameras couldn't tell the difference between the trailer of the truck, and we drove right under there. They said they think he was asleep. But anyway. So where we at? So we're on number 3. So here we come down here. And let's erase. I didn't erase all of it. No, these are not going to change right now, so I'm going to leave them alone. So over here we have a what? We have a 0 on K, we have a 1 on D, and we have a 0 on H and a 1 on D. So we'd still get a what? 0. Now it looks like the next one's going to give us something, right? Let's So our next one, I would have a 0 on K, I'd have a 1 on D, I'd have a 1 on H, and I'd have a 1 on D, so we get a 1.
Now, this is where the people part come in.
All we're trying to do, because Milton says the circuit looks different because one we're outputting on an OR, the other we're outputting on an AND. And what we're trying to do right now is we're trying to prove if the circuit works the same.
But if you finish out that those ANDs to get to the OR, you have a O and a 1. But at the end of the OR, it'll be a 1. So
Well, it's saying this or this would cause it, but we're going to see it. We're going to see it does exactly the same thing.
what is the bottom of the top is high.
Well, I know this right here is going to give me a 0. This right here would probably give 0. This would probably give me a 1, and that would give me 1. That's going to be the truth table. I can see because D's in the center and D's on both of them. Right? You understand? So that's why we get the AND, because it says, right? So here what I've done is I've got out and I've got both my key in the ignition and the lights are turned on. Down here I've got, and I open the door right here. So D is opening the door, right? So if D is a 1, and I've got, and K is a 1, or then it's going to do that. So we'll come over here on the next one, which we dropped off a whole gate. But look, this says D and D. D's got to be high on both. D's got to be, so look, A and K or what? So we'll see. It's going to have exactly the same truth table. Of course, we know what to reduce. Anytime you see this, anytime you see an input that's got the same term, odds are it's going to reduce. I'm not going to. So here's this. This is what we came up with. Now we're going to see if it's got the same truth table. HDK. So we'll do what, and then we'll call the output X. 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7.
okay, so I see you put D in the middle.
I just put D in the middle because it's easier, like on this other one, it was easy to see because I knew D affected both of them. So if I put D in the middle and then I see a 1 on, if I see a 1 on either side of D, I knew it was going to give me a high output.
So let's say that when we do draw the truth table,
You can arrange them any way you want to. It's just that to me it was easier to see.
so will it come out the same way?
Yes, it will. Truth tables are truth tables. Right?
Okay.
That makes sense? Truth tables are truth tables. So how you arrange them, I don't know a good analogy. You know, it'd be not even similar. It'd be like my house. I can go 5 different ways to get to my house. So what we're saying is that once I can arrange these in any way, and we should come up with the same truth table, because you should know that A times B times C would be equal to B times C times A, which would be equal to what? Which one? B, C, A. But all we're doing is rearranging them. So no matter how you arrange them, it's going to come up with the same truth table. It's just that when you set up your 1s and 0s, it's easier just to start with 0 and start counting. So this one might move up and this one might move down, but it's always going to be that same combination. Does that understand, Brian? So it might change the order of where it's at over here, but it won't change this order over here. So here, 0, 0, 0, what did they give me? 0. Over here it's a little easier to do because then, in fact, it would probably been easier for me to put them, arrange them in the same way that we got them up here. So let's do that. So let's leave them the same. So we'll see if this truth table is the same. I'll just have to deal with it. So, now we got what? 1 on K, and then these two right here would be 0. Well, the output would still be 0. As long as D is a 0, the output's 0. Okay. So I could come down here and do that. So the next one, D is a 1, but the other two are zeros. So this would give me a 0. Now the other one looks like we might get a 1, but let's see if that comes up and gives us that. So the 1, this is a 1, and K is a 1, and this is a 0. So this would put a 0 there. This is an OR. That'd put a 1 there. That'd put a 1 there. So the output would go to a 1. This is going to be a 0. This is going to be a 0. This could, now notice I know why this is going to be a 0. Because D's a 0. D's a 0. D's a 0. It's an AND, right? You understand? And then the next two would give me a 1 because these are ORs. So what do we notice? Yeah. So don't get confused just because you started out without putting an OR and now you're outputting on the AND. We're not looking at the circuit. We're looking at, does that circuit do the same thing? That makes sense? Because that's the way it reduced. I mean, I came over here and put the equation down here. K, so I came up here and I did the equation. And then I factored out the D. And then I came over here and I factored out the D. So it means the D came over here, D, right? K or H. Once I factored that out, that means now I look at the main divider in my equation. What's the main divider?
D.
The main divider, not the D, the main divider is AND. Don't say multiply. This is logic, right? This is not math. So it says, D, if I was to read the equation, it'd say D, right, and K or H. So when we draw the circuit, we look at what divides what's the main divider for the circuit. And that tells you what you would output on. Right. So this is basically the same thing. I know this is going to reduce. This is the same circuit. After hours, this is the alarm. So after hours and somebody opens the door, or, right, if after hours and the vault door is open, then this would sound the alarm. So I'll develop the equation. I'm going to come over here on this side. I'm going to put H, F. I'm going to come over on this side. I'm going to put H and D, right? And then I'm going to come over here. I'd say X is equal to HF or HD. This is the same circuit. So I know this is going to reduce. So I'd say X, and what do? Back out the H, F, and D, or D, I'm sorry. Now these, you gotta put those in parentheses, right? You understand that? Because it's an OR being AND. And this is the same circuit, but this is just a, so that wasn't too hard. There's the same circuit. But you got to understand, here I'm going from 3 gates to 2. Now you got to think about this. This would be a 4-input AND gate if I did it on a 14-pin chip, and I would use 2 of them, and that would only be 2 that I could use somewhere else, right? You understand? This one I would have 3 gates that I could use somewhere else. People don't understand is the only thing that those things have in common are they're in the same package. right? You understand? When I design something, when we design a big complex circuit, you're going to have a lot of ands, you're going to have a lot of ors, you're going to have a lot of nands, you're going to have a lot of knots, you're going to have all over the place. What people don't understand is they'll see this symbol, they'll see this symbol somewhere, and they'll see this symbol somewhere, and they think they got to have two ICs, but that's not true. Because why? Because there's 4 inside the package. That'd be like all of us go out there and get in a car, got to be crowded, a car together. What do we have in common? We're all different people, but we're in the what? In the same car. And we don't have to go to the same place, right? You understand? So we can divide this out. So we're reducing circuits, but what we have now is I've got 3 more OR gates that I can use what? Somewhere else without having to put another IC into my system. So that's why when we looked at those schematics, you saw a U205 over here, and they might have been one over here, right? You understand? And then I didn't give y'all out that. The last drawing on the schematic was unused gates. And this would tell an engineer if I needed to come back and modify it, I might not have to add a what? Another gate at all. I might have a spare one that I could figure out how to wire in somewhere. So will this guy reduce? No, because why? There's no like equation. There's no like terms inside that equation. I've got A or B. So see how we bring it through. So what we do when we develop the equation, we start on the inputs and work toward the what? The output. You're looking kind of strange there, Brian. But see, if I don't see any like terms inside this, even if I and that through, it's not going to give me any like terms. This is not going to reduce at all. This is the smallest this circuit could do. So just because you design a circuit don't mean it can be reduced, right? You understand that? I mean, this is why it's important. This really came to me. We bought, when I worked out at U.S. Steel, I was an electronic repairman out there. They bought an electroscale. And put it on, it was a truck scale, and it didn't have an auto zero on it. You know the problem with these big old truck scales? They get garbage on them all the time. So what you want on a scale like that is you want an auto zero, which means what? It constantly zeroes out the garbage that's on the scale. This was on what they call the lime scales at U.S. Steel. This was in the main gate. As soon as you come in the main gate, it was over there. This is where they brought almost anything that came in that gate, and they would weigh it. And what they would do is they would come in and they would weigh, and then it would print a ticket off for them, and then they would go back, and then they would come back and weigh, and then they would print it on the same ticket, and then they'd know how much to charge. Well, they didn't buy that scale with an auto zero. So what my task was to design an auto zero circuit. So the scale gave you a motion, so it gave a motion sensor on it, so something pulled on the scale. You didn't want to zero it out if something was pulling on the scale, right? So I came up with a circuit. We wanted to zero out if it was under 2,000 pounds. I mean, this was a big truck. And you'd zero out like every 10 seconds or every minute or something like that. I don't remember that, but it would zero out. The problem is I came up with this big old circuit, and it would have worked fine. I went in and showed it to my boss, and he said, well, Rich, let's see if this thing will reduce. And guess what? So I went from a circuit board that would have probably been that big down to a circuit board that was like that. And it worked. If they still have that electric scale out on the line scale, probably still got Rich's circuit. But we reduced the circuit, and it really was a simple circuit compared to what I had. Huh? Yeah. So that really showed me the what you could accomplish with this. Plus, we can come up here, guys, and you can put ones and zeros into your equation, and we'll show you how to do that. And you can figure out what the output is without a truth table. So you can figure out what the output would be without a truth table. You know. So let's see if we can do that just for the heck of it. So let's come over and let's just throw something random up here. And then I could come in my truth table. I'd say X would equal to A. What do I have A at? 0, right? Then I'd say and B. I'd have a 0. Of course, I know that's going to be a 0, right? Okay. And then I'd say OR. And then I'd say what? C is a 1, right? Then I'd say M would be a 1, right? And then I'd say, if I lost something yet, or N would be a 0. So I'd say, okay, 0 and a 0 would give me a 0. 0 and a 1 would give me a 1. This right here would give me a 1. So the output would be a 1. So I can see that. Now I can come over and try to take this through here. I know this is going to be a 0. I know this is going to be a 1. I know this is going to be a 1. That's going to be a 1. That's going to be a 0. But I didn't have to go through that because I just plugged that into that equation. So what we're saying is if you got a situation going on and you got the equation for the circuit, you don't have to do a truth table. You just take what you got, right? You understand, plug it in that equation. If it comes out to be a 1, then you should have had a 1. If it comes out to be a 0, you should have a 0. So that's another advantage of having it. Because my truth table would have how many in it? No, there's no repeats, right? A, B, C, M, N. That sucker's got 5 inputs. This truth table would have 32 combinations on it. If I did a truth table for the circuit, and we can do truth tables for circuits just like we do truth tables for gates. So now I got a 32. So it'd take me longer to do what? Write it out than just plug it into the equation. Will this one reduce? No. This looks like this is the best we can do. Are we okay? These are some laws, and this is, let me find my handout, guys. We'll take a break. I got the handout. That's somewhere. So. By my house. Oh, there it is. Most of the rules should make sense. Because this is, a lot of the rules that we use in Boolean algebra are basically the rules that we use in basic algebra. Except we don't have any squares. We don't have any square roots. And it's all ands, ors, right? Ands, nots, and ors. So it says we can rearrange ors. We can put them in any order, which makes it easier to solve them if we can get like terms together, right? So that's one of the first things you learn when you reduce an equation in algebra. If you can move the equation around to get like terms together, it makes it easier to reduce, right? So he's saying, of course, we use this. Sometimes we use this just to group them. So we not only do this to and, if they're directly together, then this means and. If there's an or between them, that means we're just using this to group the group. And like they're saying, you know, if you got addition, what can you do to the terms? If everything's addition, you can move them suckers around any way you want to, and you can group them any way you want to. And that's basically what they're saying here. Here's what they did is they and through, just like, but it's and through, it's just like, right. Well, we're not multiplying, we're anding. If you have the symbol for multiply, it's and in logic. And if we have the symbol for, the symbol for addition in math is a symbol for or in logic, or in Boolean algebra. And sometimes what we do, and you learn this in algebra, is you expand an equation out to do what? To see if it would reduce. So we have no we have no, so if I came over here and this is going to be later on, if I had A times A in math, we would say this would be A squared. But if you come over here and you say A, so that would be the same thing. So A and A is going to be equal to A, right? You understand? We don't have any squares. So B or B would be equal to B, right? You understand that? We don't come up with 2B, right? Like we would do in math. So in math, if you said 2B plus 2B, you'd say that would be 4B. That makes sense? So there's no such thing as 2B. We might have a B or B, or a B or B would be a B, right? That makes sense?
Why are those A's negative?
What do you mean? There's no negative. There's no negative. This is just the separator. I'm sorry. That's the bullet thing that PowerPoint gives you. Good point. So these are going to be on this sheet right here, by the way, somewhere. So that's what they're saying. You know, the cumulative law in your book, they're giving you saying, okay, this is equal to this. So if I've got ORs, I can arrange the inputs any way, right? I can group them any way to get them to put like terms together so I can see if they're reduced. If I've got ands, I can move. So over here we have ABC, which would be the same thing as BCA, which would be the same as what? BAC, all those would be. So we can move these equations, move these around. Multiplications, we can rearrange them to get them the way we want to. Not multiplications, ands, we can move them around to get them the way we want to. And ors, we can move them around to get them the way we want to. And so these are all the same things. These are just drawing the circuits, guys. So rule 1, anything and with an and is a what? I'm sorry, anything and with a 0 is a 0. Yeah, I mean we can, and most of the time, most of these rules you can see in your mind. So if I come over here and I say I got something called A could be anything. And then I come over here and I put a 0 right there. I don't care what A is. It's an AND gate. If I see a 0 on one input of an AND gate, guys, the output's going to be 0. So A could be any combination. It's just very, I mean, I could come over here like this, and this is the same rule. So I could come over here and say, you know, A, B, C, D, E. Down here I'm going to say this is a 0. Well, what would the output be? Well, this in this equation is substituting for that A. So that means no matter what A is, if I AND anything with a 0, it's going to give me a 0, right? That makes sense? Anything AND with a 1 is going to be whatever you AND it with. Y'all understand? Yes or no? That makes sense? Well, come over here. I'll come over here and I say, so A, I'm going to come over here and I'm going to put a 1 over here. So let's put it up. Let's just put plus 5 volts. Well, if A is a 1, the output would be a 1 if A, and this is A. If A was doing this. Well, every time A went high, the output would go high because I got all highs. Every time A went low, the output would go low. So what it's saying, if I AND A with a 1, no matter what A is, the output will be what? Will be whatever A is. Here it says A ORed with a 0 is going to give me what? A. Because that's an OR. It says any, right? You understand? Here it says A ORed with a 1 would always give me a what? A 1. Because I'd always have that any, right? You understand? So I've come over here and I draw this circuit. And A is doing this. And over here I've got a 1. Well, what would the output? Well, we've always got a 1, so the output would always be. And these are the circuits I just showed y'all. Rule 5, anything and with it. So there's no such thing as an A square in Boolean algebra. A and with A would be A, right? That makes sense. A ORed with A would be what? A. A and with not A would always be 0. Do y'all understand that one? So the bar means not, by the way. Y'all okay on that one? Yes or no? Okay. Huh? Yeah, well, this one right here, I would come over, let's say I'm going to bring A in. Down here, I'm going to put not A, so there's not A. Well, there's no way in the world I'd ever get a high out of that sucker. Why? Because if A was high, my other input would be low. If A was low, my other input would be high. So that's what they're saying. If I ever see A and with not A, then that means that's going to be a 0. A and with not 1, A ORed with not A would always give me a what? 1. Y'all understand that one? Y'all need to see the circuit. Huh? Yeah, so always, 1 would always be a 1, right? Okay. This is rule 9. These gets a little more complicated. So we could do the truth table. A ORed with not AB would always equal to AB. And then not A ORed with A and B would always come out and give me not A or B. And these are the 10 rules that we'll look at. We're not going to use the bottom one very much. So A in a double knot. So if I come over here and put a 1 right there, what would that give me? 0. What would that give me right here? 1. So what they're saying, if I came over here and did this, what's that going to equal to? That makes sense? Yes or no? It's just like a double negative. In math, a double negative is always a what? Positive. So here, that's basically saying the same thing. And we'll say we're going to use this circuit later on. About the only time you ever see this circuit. So what would we use this circuit for? First of all, guys, what you got to understand, there's a gate that has this symbol right here. So what logic does this guy do? No, this is an inverter. I got 2 symbols for an inverter. I got this one, right? Or I've got this one. What logic does that guy do? There's no bubbles on it. How could it be a knot? So it says if I get a high in, I'll get a high out. If I put a low in, I get a low out. But what logic does it do? Say none. There's no logic. Yeah, well this guy, we refer to this as a buffer. And this guy, you'll see it used all the time. Because it's got a function in life, it just don't do any logic. No, we can't change the way it's flowing. I don't know if I understand what you're saying. It has a function in life. It's just like in motor controls, you're going to learn this contact right here doesn't do any logic, but it's got a what? It's got a function in life. These guys right here is a buffer. It's a go-between. We'll use a bunch of these going from my big computer or whatever, going out to the outside world. Because if I let something get into my computer, it could tear all kind of stuff up, right? Here what I do is I'd lose a buffer. So it's a lot easier to replace one buffer than it is to replace everything else, right? So you'll see these things used a lot to buffer inputs from the outside world into my computer or our outputs. And also we use them to increase what we call the fan out. And we'll talk about that later on. So it's got several functions in life. But, so that's a symbol. And I think one of your labs is going to ask you what's the difference between 7407 and a 7404. Well, one of them's a buffer and one of them's an inverter. And that's going to be in one of y'all's labs, right? So y'all ready for that, right? But what you need to do is look it up in the data sheet And up in the right-hand corner of every data sheet, it tells you the name of the gate. It says it's a 2-input AND gate or whatever. These are just truth tables. And these are the same rules that I basically gave y'all out. So will this guy right here reduce? How do you know that, Brian? Okay, so it looks like it'll reduce, right? Why? Because C goes to 2 different places. So C not only goes here, so you need to follow this too, guys. C goes over that. So C goes to 2 different places. So it'd be like I come all the way back up here instead of doing the stupid thing that they're doing. What was that? Right here. So technically I could have came over here and did what? Brought this out and hooked it together and called it what? After hours. I need to recalibrate my screen. Because those two are what? They're the same thing. So when you do these things, you got to follow the circuit through and see if the term goes to 2 different places. Well, let's see if we can do the equation for the circuit. So this would be B. Everybody okay so far? This would be what? A or C, and I'm going to put it inside parentheses so I don't. Then I'd come right here, I'd have B, right? And A or C. Are we okay so far? Lost anybody? Then I'd say X is equal to B. My computer keeps unplugging itself. Oh, I'm going to do it. A or C or C. That would be what X is. Everybody see how we got that? Yeah. And then what would I do? What would you think I would do to go? What would be the next step I would do? Well, C's already by itself. What I would do is get rid of this thing right here. So I would say X. I would go ahead and through. So this is going to be BA or BC or C. Now I can isolate C, right? You understand? So this is one of those things where we had to spread the equation out to do what? To see if it would reduce. Now what would I do, guys? I'd say X would be equal to BA. Then I would factor OR, right? C or B or 1. Well, what I'm doing is I'm leaving that one and I'm playing around with this guy right here. And I factored out the B. I'm sorry, I factored out the C because C's in both these terms, right? You understand? Okay, so what's anything ORed with a 1? Itself, right? No, anything ORed with a 1. Y'all look at y'all's rule. B, 1, what would the output be? Yeah, there's always going to be a 1. So anything ORed, if I OR anything with a 1, the output will be a 1. So this would be X would equal to BA or C and 1. Anything and with a 1 would be itself. So X would equal to BA or C.
I don't like this already.
This is just math. This is just what you would do if you were taking algebra. I mean, we hadn't done anything different here than I would reduce that if I was doing if this was math. But it's Boolean algebra. So the first thing I did is I came up my equation. X equals to B and A or C. Or C. I can't isolate C because C's inside these brackets right here, right? You understand? So I can't pull C out yet until I get it out of those brackets. So what did I do? Well, I and through with my B. So when you and through, you take this and just combine it with that, and you take this and combine it with that. Right? You understand? So if I combine that, I'm not getting rid of the or. That's going to be A, B, or B, C. Then I've still got what? I've still got that, and I've still got that. Now what do I notice? On the right-hand side, I've got what? 2 C's. Right? Yeah, well, we got either way to go, but I guarantee you, if we did it both ways, it would come up with the same answer. Well, let's see. So let's factor out the B. So that's going to be B is equal to what? A or C, but that's what I started off with. So why would I go back to what I started off with? Understand? Yes or no? So what we're saying is that this is what I started off with. If I factor out the B, I started off with what I started off with. I end up with the same circuit. That makes sense? Yes or no?
Sure.
So I come over here and I multiply through B. So X. So I'm trying to see if it'll reduce. I'm trying to see if this will reduce. So let's say I and through with B. So that's going to be BA or BC or C. And you're telling me I've got 2 B's. Well, okay, let's factor out the B. X would be equal to B. X would equal to B or A or C or C. Oh, dang it, Rich. So I factor out the B. Okay, so B would be equal to A or C or C. Well, what did I just do? Yeah, so I came back with what I started off with, right? So what we're going to do is we're going to leave that alone because that's just not going to do anything for me. So this is, I just did this to get that, but I noticed I got what? 2 C's. So I come over here and factor this out. So X would be equal to B, A, or C, C, right? This would be B, oh, sorry. Thank you. C, or 1. Right? Okay. And then I know that C or 1 would be equal to a 1, right? That means X would be equal to B, A, or C. B, A, or C. Yeah, you'll have to stand out right. And the only reductions that you'll do on the test will be bonus. Which is what they should be, right? Because in this class, all we're trying to do is see the power of Boolean algebra. In fact, when you do the lab on Boolean algebra, all of the circuits have been reduced for you. And what you're going to do is you're going to wire up the big circuit and do the truth table. You're going to wire up the smaller circuit and do the truth table. And what should you find? The truth table should be the same, but it's going to take a lot of IC. So what we're saying is that in this class, it's not extremely important if you know how to do this. But if you want that 5-point bonus on the test, then you need to pay a little bit of attention, right? So this is that's what it is, 5-point bonus. But you need to know how to develop the equation for the circuit. That's not going to be a bonus. and you're going to need to know how to take an equation and come back to the circuit. That's not going to be a problem. Because that's shouldn't be that hard, right? As hard as trying to reduce this down. I'm sure y'all loved algebra. But what we did now, this is algebra. We did what we would have done in algebra. Exactly this, there wouldn't be any difference the way we would reduce this. Because we didn't have any A's and A's and C's and C's and stuff like that. And of course in algebra, C or CR1 would be equal to, right? Wouldn't be equal to a 1, it would be equal to C. So that's a big difference in algebra, not in logic. I mean C plus 1. So with this one reduce, yeah, we got A going all over the place. Let's see if y'all can do the equation for the circuit. So try to do the equation for the circuit. Yeah, B goes all over the place, A goes a couple places, so this guy here will definitely reduce. So see if y'all can do the equation for the circuit. Get your pencil out, see if y'all can do the equation for the circuit. Right? See if you can do the equation for the circuit. No, let me get the circuit back up here, guys. My mouse wasn't working. Yeah, so yeah, if y'all want to shoot it simplifying, that would be great. So this is going to be A or B, right? And put inside parentheses. This is going to be B and C, right? And then this right here is going to be A or B and B, C. Okay? And then the output, X, would be equal to A, because A is coming all the way over here, right? And then I would say or A or B and B, C. Oops, didn't it? I usually do it when I have ORs just to keep them grouped together, because sometimes it'll and sometimes it don't, and sometimes we can leave it off. But I just put them in. I put all my ORs while I'm working through my circuit. I put my ORs in parentheses. That's just I learned a long time ago, because then it turned out that I couldn't drop it, right? Because we ended up with what out here? Yeah. So you can group these things, and that's what you're saying. So if I come over and I say, if I had B, C, A, or B, then that would be, I couldn't do anything with that, right? But if I said B, C, so this right here indicates and. But if I come over and said B, C, or, right, then I could come over here and group it like this, and this is no longer an and because it's got the or in there. And all I'm doing is using the parentheses now just to group them, so I can keep them together, right? Understand?
Now let's say test time. Will that suffice, or we have to add to simplify?
No, like I said, on the test, there's one that asks you to simplify, but it's a bonus. But developing the equation for the circuit, and you might have came up with this. You might have come up with X is equal to B, C, A or B or A. Well, that's the same dang thing, right? You understand? So as long as you got, it depends on which way you come through and how do you combine them. So I could have just as well put BC first right here, right? You understand? And put A or B right there. And then I could have brought this through first and put my A, but this is exactly the same thing. And that's what they're saying. If we understand this, we know that these equations could be rearranged, right? You understand? It makes them easier to. So what would I need? Would this reduce? Yeah, I imagine it will. Yeah, but we got to get this guy out of this group right here, right? You understand? So we'll take the BC through. So X would be equal to ABC or AB, or A. Did I mess up somewhere? No, I'm sorry. I messed up the second one. I need to take care of me sometime. So A, B, C, or B, B, C. Is that right? B, B, C, or A. And we could reduce, so X would be equal to A, B, C, or B, C, or A. So B and with B is B, right? Now, of course, what I would do now is I see I've got B's, but I just spread them out. The BC's and the BC's, we could factor that out too, guys. Looks like it. Or I could also factor out the what? The A. Let's factor out the BC. Is this right?
No, it's not. Not that I know of. I don't look.
I got this right?
No.
So B, A, B, C, B, B, C, or A.
The BC with the AB makes it look like a and instead of the actual or what it was.
Well, if I just drew this circuit alone, that circuit right there represents this. Oops, sorry. So it's not one gate, it's the output of two gates, right? Understand?
I don't know.
Then we AND this through. So which one do you like better? Each one of them would work. That one better. But understand in math what you can do, and like I said, it depends on which way you decide to come through. But the equation itself is exactly the same. Oops, I didn't want to do that, really. So what we're saying here, I'm coming through this thing, and I say this is A or B, right? And then I come down here and say this is BC. Well, what if I'd have took the bottom one through first, and I said this is BC, right, and A or B? Is that the same thing? It's exactly the same thing. So what I'm saying is that no matter which way you bring the equation through the circuit, right, you understand, this equation and this equation are equal to each other. It's just been what? Rearranged, right? Understand? So we can reduce the top one. So the top one says X is equal to A or AB and BC. So I can't reduce anything now because I can't just do an A inside those parentheses by itself, right? So we're going to AND through. So X would be equal to A or A, B, C or B, B, C. Everybody okay there? Yes or no? Okay, so far. Okay. Then I know for a fact, if you look at your sheet, I know a fact that B and with B is equal to B. So we can drop that one out right now. So we'd say X is equal to A or A, B, C or B, C. Now I got two options here. I could factor out the A or I could factor out the BC. Which one y'all want to do?
Take away, Rich.
Well, let's factor out the A. So I'd say A, X is equal to A, right? Right? This would be 1, because I pull the 1 out right there, or BC, right? Right? Okay? Or DC.
So let me ask you this.
So X would be, this would be equal to 1, X, A, B, C. A. Go ahead, Brian. It's Brian. You need to call y'all 1 and 2, Brian. Now plus, or. And it's hard to get used to. Y'all hear me do that every once. Let's take the other one and see if we come up with the same thing. X is equal to BC, A or B or A. X would be equal to A, B, C or B, B, C or A. That's a B. Factor out the BC, so it's the BC, A or 1 or A. So X would be equal to B, C, or A. And it just came up backwards, but it's exactly the same thing. B and C or A. Yeah, but what I'm saying is that we factored that we did it both ways depending on how you trace the circuit through. I combined the step, by the way. I don't know if y'all noticed that. This would be equal to BD, right? Would be equal to B. So I went from 1, 2, 3, 4 gates to what? 2. Now this next one is what got me. When I was thinking I had to look at all the outputs of the counters that was feeding the display. I thought we had to look I thought I had to look at all the outputs, and then when I reduced the circuit down, and we realized that we didn't have to do that. So what you're saying is you might come up with a complicated circuit like this. But this is what you got in your mind, right? This is the way you see it. So you come up here and I say, okay, this is what I need. I need this and this and that or this, and you come up with this circuit right here. And you wire it up and you see how it works. And you say, well, let's see if that thing will reduce. And then when you reduce it, you realize you were monitoring an input that didn't even have to be monitored. And that was my problem. I was monitoring all this garbage that when we reduced it down, there was several inputs that had nothing to do with whether the output was true or whether the output was false. So what I did, this guy here went from what? Went from 1, 2, 3, 4, 5 gates over to 2. And then I saved a whole wire. I didn't even need to hook up the A input because it has absolutely nothing to do with the operation of the circuit. But when I designed the circuit, that's what I visualized it doing that. So let's see if y'all can do the equation for this one. What's that? What you got? No, I didn't throw it in there. This is in the book. In fact, the book might have it solved for you, but I think the figure numbers are still the same. I think you got your book right. Is this the same figure? Which makes it easier, especially on a circuit like this, because you're constantly doing one. All right, y'all see if y'all can just do the equation, guys. See if you can do the equation, Brian. There you go. Oh, yeah, I see that. Yeah, so there's two. It comes up through here, right? Are we okay right there? Where? No, there's no, this comes in,
Oh, it is two.
it comes in on the other side. Yeah, but you say you digress. So everybody okay here? Does that look okay? And then right here we would have not B, A or B, right? We okay there? Yeah, because of the and. Can y'all see that, or is it blurring out? Then X, depends on where you start at, would be it not B and A or B, or not B or B, C. That's our equation. Of course, you could have, it could be rearranged, right? You understand? There's several ways you could do that, depending on which way you'd have came through. If you'd have started at the bottom, then the equation would have been BC, or not B, or, oops, it could have looked like this if you had came up through the bottom, right? And those equations are the same. So right off the bat, before I do anything, I could get rid of the what? Well, on the right now, I can get through with the ones on the right. So I could say X is equal to not B, A, or B, or, no, can't get rid of that yet. Well, I can. Let's look at our rule and see if there's a rule that lets me get rid of that one. The rule is rule number 10. Nope, it's not rule number 10. Oh yeah, it is. Or, see the or right there? Look at rule number 10. Follow it over to it says or, where it says not X or X and Y equals not X or Y, right? You see that? Rule 10? Yes, no? What else can we do? We could do the truth table, but what we did is just looked at one of our rules. So I looked at rule 10. You can't rule 10? What we're looking at is we're looking at this. It says if I see this right here, if I see not X or XY, then this is going to be equal to not X or Y. Well, what I'm going to do is I'm going to substitute mine in there. B, not B, or B, C. See, that's exactly the same format. So it says we can replace that with what? Not B or C.
But let's say, so let's simplify it that way. How will we know how to draw the actual diagram?
Well, what we're doing is we're going from the circuit. We're going from the circuit to the Boolean equation. You're asking how do we know how to draw the Boolean equation from the circuit from the Boolean equation? So what we would do is we would look at the equation and we'll look at the main divider inside the equation. It's OR, right? You see that. So here's my main divider inside the equation. So y'all write the equation down. And we'll just keep. So what's the equation? X is equal to not B and A or B or not B or B. So what I would come over here is, if I was going to draw the circuit for this equation, I'd look at the main divider. The main divider is an OR, so I know I'm going to output on an OR. And then I would follow it back this way. So I'd say on one input, well, we do the same way.
But you see how you got from the not B to not B or C, you drop the actual B itself. Once you drop the actual B itself, how do you know to go back to not B plus B, C?
Well, you don't. If you drop it, it's gone out of the final circuit. It's gone out of the final circuit. It's not gone out of the front circuit. It's gone out of the final circuit. So we don't know how to draw the final circuit until we come up with our reduced equation. Once we come up with our reduced equation, then we would draw the circuit that represents that equation. Okay. And it would have exactly the same truth table. So we're not through. Yeah, we're not through yet, because I can see this guy here is still going to reduce. I just did one thing. I see B's in here and I see B's in here, right? You understand? So I got to say, well, let's see if we can reduce this any further. So what would we do? We'd go ahead and AND through, right? So I'd come over here and I'd say X is equal to not B A or B or not B or C. Well, what we'd do is we'd say, okay, I got two not B's in there, and I know if I can get rid of, so I'm going to rearrange my equation. So I'm going to see A would be equal to, So I would say A would be equal to not B or, don't let me go, guys, gotta watch me. Would equal to not B A or not B or B or C, right? I got that right? All I did was got my not B's together. So it says we can move them around. I can factor out the not B now. So not B, right, would be equal to A or 1 or B or C, and A's gone. Because anything ordered with a 1 is a 1, right? So X would be equal to not B or B or C. Well, what I just showed y'all is A is gone, right? You understand? A just left. Now we got to figure out what to do with the B or not B.
So
this is going. That would be equal to B, right? So X would be equal to B or C. I think we left something out, but
I don't think that you simplify. So you can't simplify a not with a standard. You know, that like a not B.
Yeah, well, let's go back and look at our rule. So I come up here somewhere and I should say,
okay, so it's
rule number 8. I'm sorry.
Okay. Yeah, it's A.
Yeah, so we went somewhere wrong. So eventually, this is what we're supposed to come up with right here. But what I wanted you to see is that when we started reducing this thing, what happened to A? It just disappeared. So when I designed my original circuit, I thought I had to monitor 3 things. But it came out I only had to do what? Monitor 2. So this would take us from a circuit with 5 over to a circuit with what? Circuit with 2.
And we would never go from the circuit with 2 back to the circuit with 5.
No.
Because there's a lot of things that dropped off. There'd be a lot of gates.
So this is the one we would build. So originally in my mind, when I was setting this thing up, I said, okay, I need to monitor A, I need to monitor B, and if A is true and this is true and B is not true, and that's what I came up with in my head, right? And I drew the circuit out. Yeah. And then I said, okay, let's see if that circuit will reduce. And then then it reduces down to this, and this is the one I would build, and this is the one I would sell because it does what? Does the same thing, but with instead of using 5 gates, it ended up on using what? 2. So that's the power of Boolean. So if you design a circuit and you can build equation, if you can come up with the equation for the circuit and it won't reduce, and that's the best you can do. But if you ever come up and design a digital circuit, the first thing you should do is come up with an equation, right? You understand, and see if it will do what? Reduce. So here I'm an engineer. The other engineer's putting 5 in there, right? He's paying $1. Here I'm putting 2 in there. I'm paying 50 cents, right? You understand that, or even less. What can I either do? Well, if I sell mine as the same price as my competition, I'm going to make a lot more money, but that's probably not what I will do. What will I do? I'll sell mine for less, and it does exactly the same thing. So which one would sell the most? Unless you're the kind of person that buys things because of the name brand, or buys a phone that does 5,000 things more than you ever use it for. So my wife's got a phone. She plays, she gets on Facebook all the time. She likes to text. We text each other all the time. That's the main. But she's got a phone that does a lot more than she would ever need. And this one would have reduced down the same thing. So here the gate, there's 5 gates out there. And when we go through all the Boolean algebra and reduce it, it came back down to what? 1 gate. So this would be really, really drastic on something like this. But what we're trying to do in this lecture is we're not trying to teach you Boolean algebra. We just don't have, we could teach a whole course on Boolean algebra. It's just like you take a whole course in what? In algebra, right? Of course, you do a lot more things. What do y'all still do? Y'all still do graphing equations in Algebra 1? Huh? Graphing equations, reduction, but the main part of the thing is learning how to reduce equations, because if you can reduce a math equation, it makes the equation what? It makes it easier for not only you, but for whoever you pass that dang thing down to. But here, the math, when I was in high school, I did very, very poorly in math because it didn't make any sense to me. Because why solve for A? And then when I got in the Navy, they decided I needed to get into electronics. All of a sudden, math made sense. Why solve for A? So you come up here and you do the math and you take your meter and put it in the circuit and it worked. After I got into that field, I aced every math class I ever took because now the math made what? Made sense. I knew why we needed to deal with infinity and calculus, why we need to do integrals and why we do differentiate and all that kind of stuff, because now it did what? In my the math instructor that I had in college, Mr. Tate, he taught calculus. He would give out, that's what he would do. He'd say, well, I'm on top of a building and I weigh 200 pounds and I've got a rope that holds 120 pounds and the building's on fire and I got to slide down that rope. He says, how fast can I slide down that rope and how much friction do I need to put on that rope to slide down that rope so the rope don't break? And that's the kind of calculus, that's the way I learned calculus. So he taught me real life scenarios, right? It was funny. He says, well, I'm not going to tell you some of the stories he told. So everybody okay here? So y'all go ahead and take a 2-minute break, guys. Has a what? OR function, and every OR has an AND function. And to convert between the one, when we put the bubbles on the input, we call that negative logic. When there's no bubbles on the input, we call that positive logic. So every positive logic symbol has a negative logic symbol, right? You understand? And that's why all the 5 basic gates actually has 10 symbols that we can use. And this is what they're showing us. Are we okay? Morgan's theorem said break the bar over the variable and change the signs between them. Inversion bubbles used to show the inversion rather than invert errors. Use parentheses main for a proper grouping. We already know that. And some of the products. So basically, most digital circuits end up with either outputting on an OR outputting on an AND. Or this could be a NOR, or this could be an AND. And I know it's not correct, guys, so I could come over here and I can feed this anyway. A circuit that outputs on an OR, we usually refer to this as the sum of the products. Inputs on ANDs, let's rephrase that. Any circuit that inputs on ANDs and outputs on ORs, this is referred to as the sum of the products. And so inputs on, let's just draw a circuit. So I come over here and I put it like this. So let's just make it pretty simple. And most digital circuits can be put over to this format. So we can swap things around. So I can turn ANDs, I can turn a positive AND into a negative OR, right? You understand? So what we're saying, I'm going to do all positive logic gates. Almost all circuits that come up with made from the basic gates, we can set it up in either one of these formats. This, since we're outputting off of AND, this type of circuit would be called a product of the sum. So they're doing what we shouldn't do. They're saying ANDs are multiplications. So the answer to a multiplication problem, we call it the what? The product, right? The answer of an addition program, we call that a sum. Well, they've given these names of these circuits basically like math, but they're not truly. So this circuit right here, since we're outputting on this, they're calling this the what? Sum of the products, or they call this a SOP, not SOL, right? SOP. And then they call this POS, so positive. So if I've got a basic logic circuit, I can convert every AND in some type of OR function, or I can convert every OR into some type of AND function, right? You understand that? So we can set the circuit up as either a sum of the product or a product of sum. Now, where does this come into play at? Well, the only place this comes into play at that I know of is if you play around with Karnaugh maps. So if you use Karnaugh maps to reduce it, then the circuit is required to be in what form? Sum of the product. And that's the only place I know you would concern that. And I don't teach Karnaugh. So a sum of the product means we input on ANDs and output on ORs, right? A product of the sum means we output on ANDs and inputs on ORs. And notice using this De Morgan's theorem where I can swap gates around. So I can make an AND have an OR function, right? You understand? Or I can make an OR have an OR function. Have an AND function. So I can take a digital circuit using the 5 basic gates and I can put it in a sum of the product form. And this is the only way I know that makes sense if you use Karnoff maps. But Karnoff maps, guys, is you come up here and you set up these cells, and then you take these cells. So if I had a 5 input gate, that sucker would have 32 cells in it. And then I'd match ones, I'd group them, and then we could eliminate them. It's really neat, but it's about as useful as truth tables. So that's why in truth tables, we're probably never going to go over 4 inputs. Why? Because it gets so dang complicated, right? Like I said, later on, we're going to use an 8 input NAND gate. Well, how many entries would an 8 input NAND gate have? It would have 256 entries in a truth table. And it said, just to know that all highs equals a low, right? You understand? So the expressions are a lot better to do than truth tables. We use truth tables just to prove that you understand the circuit. If you can do a truth table, if you can do the expressions, if you can write the Boolean equation, then that means you understand how, for that circuit, that means you understand the circuit pretty well. And like I said, the reduction is fun. It's fun to deal with. You know, well, I'm not going to say that. If you like math, Boolean algebra is really fun. If you don't like math, it's not. But this is all De Morgan's theorem says. It says an AND will complement to a what? A NAND will complement to a negative NOR. And how do we go between the symbols? Or vice versa. A negative NOR would complement to a positive NAND, right? You understand that? All we do is do what? We call it pushing bubbles. We take the symbol, right? And we draw the other symbol, and then if it's got a bubble, we do what? We leave it off. If it doesn't have a bubble, we add it. And that's how simple it is. But the expression is different. So this gate right here, but notice the truth table is what? The same, because it's the same gate. It's just what function it serves inside the circuit. But this gate, what would we say? We'd say all highs to get a low. If it takes all highs to get a low, then if any input goes low, the output's going to do what? It's going to go high. And that's all De Morgan's theorem says. So De Morgan's theorem only says what? That every gate has a what? Every basic gate has a negative function. In fact, even inverter has a negative function. We just don't give it a name. We call it a negative not. So if I saw this in a circuit, I'd say, well, that gate is looking for a high to get a low. But if I came over and drew it like this, we would say that gate's looking for a low to get a high. But that's the two symbols. So all the 5 basic gates, but an inverter is an inverter. We just call it, one of them we call it an inverter, the other one we call it a negative not. That makes sense? And that's the Morgan's theorem. Yeah. So what does Boolean algebra do for us? Well, one thing, so what's nice about this, of course, so how many inputs would I have in my truth table? No, right here. 8. So if I came up here and did the equation for that, so I could write a truth table for it. Or I could come over here and I could say this would be what? BC A, I'm sorry, wrong side, Rich. And then my equation would be X would be equal to B, C, or A. And I say, okay, what's this going to go, what should I expect? Of course, we can see this real fast, right? But understand, we can put this in a pretty complex instruction. What would I expect if I put that on the input? Well, I can come over here and put that into my equation, 1 and 1, right? Or a 0. So what's 1 and 1? 1 or 0. What's 1 or 0? A 1. So I know right off the bat that the output of this gate with that combination would give me a 1 without having to do a truth table. So what we're saying, if you have the equation, you can put, if it's got 15 inputs, right? You understand, if you got the equation for the circuit, you could write the inputs and put it inside that equation, and right off the bat, you'd know if it's going to give you a what? A 1 or a 0. So that's a really, so Boolean algebra is really neat, especially if you're an engineer and you're designing circuits. So what I want you to be able to do is to take a circuit. Let's make up an equation. Let's see if I got one in here. So let's say x is equal to, let's say A, B, or C, or D. Let's draw the circuit for that. What's the main divider inside the equation? Or. So I'm going to output on a what? Or. Okay. Then it says C or D. Well, this is an or, so I can bring in C or D just like that, right? But this I got to do what? Add them together. And that would be the circuit that represents that equation. So what we do, first of all, is we decide what we output on, right? You understand? And how do we do that? We look at the what? The main divider inside the equation. And the main divider, that's what we're going to output on. And then we feed the inputs into that. So we could just make up an equation and we could do just about any circuit on that thing. So let's see if we can do another one. Oops, I need to erase that. So x equal. What are you going to do, Kelvin? What do you want to do? X equal. Okay, just not B? C. What are you going to do, Brian? How are you going to do, Brian? Now we don't want to come up with something that's going to reduce. So let's do different. So we're already using D, we're using C, A. Huh? Just one? Let's put D and E, right? So we know we're going to output on the OR, right? Concrete. Go. H. Oops. Well, instead of making it an OR, let's come over here and make the last one just and all these together. But we can see our main divider is a what? OR. And I've got what? Exactly right. I've got 1, 2, 3, 4 inputs on this guy. 1, 2, 3, 4. So let's do the first one up here. Yeah, A's gonna come in by itself. Maybe. We're gonna bring the inputs way back here so we can draw this circuit. So I'm gonna come over here. This is gonna be and. I'm working from right to left. I'm gonna come up with B, bring it through an inverter, right? Then come in directly with C. Then we'll come in directly. Let's see, B, C. Come in directly with A. Then I'm gonna come in here. I'm gonna have an and, right? Let me move it over a little bit. So we'll keep our inputs at about the same spot. And we're going to bring what? DE. And then we'll come up here, then we got another and. So 4 input, right? 1, 2, 3, 4, F, G, H, and I. So what we've done is we've taken I gotta look it up, right? We've taken an equation and turned it into a circuit, right? And then of course, let's do a product of the sum. So I'm gonna put these together so let's put A or B, right? And C or D and BC. So I'm using B twice. I don't use B twice because that means it's going to reduce, right? EF. Of course, I don't have to divide that up. EFG. So what's our main divider? And, right? And then I come over here and I deal what? Or A or B. And then or C or D. And I should have, I'm going to just extend this one side. That don't look good, but that's okay. And then E, F, G. Normally what we do this, guys, we draw the symbol in the center. E, F, F, G, and then this guy would be drawn in the center like that. And everything should touch. So that would be the circuit that would represent that equation. So being able to develop an equation for a circuit, or take a equation and develop the circuit, would be what we want to do. Like I said, on the test, there's going to be a reduction on the first part, but it's going to be a long. It's going to be a bonus, right? You got any questions? Yes, no?
No.
Or you don't know enough to ask questions? This is our new sheet. This is our new sheet, so we need to understand these. Everybody okay? This is implementing De Morgan's theorem over this. So this is what the De Morgan's theorem says. It says every positive gate has a every positive logic gate has a what? Has a negative logic function. So an AND would complement to a what? OR, right? And then an OR will complement to a negative AND. A NAND will complement to a negative NOR. And then a NOR would complement to a negative NAND. And then a NOT would complement to a negative. And that makes this guy right here basically an illegal equation, but there's nothing we can do with it. So this guy says, the AND says all highs equal a high. The negative NOT says any low equals a low, right? So what do you do on these things? You just take the expression and just roll everything over. The biggest problem that we have is people looking at this guy right here, and because we teach these two guys right here first, and they think if you put a bubble on the output, it makes it an AND or an OR, but that's not true. What determines if it's an AND or an NAND? No, I'm sorry, a NAND. So I got a NAND, right? You understand? And then I got a negative NAND. Then I got a NOR. It's not. I'm trying to determine what moves it from these guys, whether they're negative or positive, right? What differentiates between a negative NAND, a negative NOR, and then a regular AND and a regular OR? Whether it's a NOR, NAND, NOR. What makes it NORs and what makes it... I think I've got y'all confused. NANDs, ANDs, and ORs, whether it's a negative NAND or a negative NOR, the active state of the input and the output are the same. NANDs and NORs, the active state of the input and the output are opposite of each other. So look, understand what I'm... If you don't have bubbles on both sides, it's going to be either an AND or it's either going to be an AND or an OR, right? If you have bubbles on both sides, it's going to be a what? Negative AND, right? You'll understand. So what I'm trying to say is that what makes it between ANDs and ORs, whether it's a negative NAND or a negative NOR or a negative AND, understand, is that if the input and the output state is the same, it's going to be a what? NAND or NOR. I'm sorry. If the input and output are the same, it's going to be an AND or an OR. If the input and the output are opposite, it's going to be a NAND or a NOR. Right? If it don't have bubbles on the input, then these are going to be ANDs, ORs, NANDs, NOTs, and NORs. If it has bubbles on the input, then it's going to be negative NAND, negative NOTs, right? Negative ANDs and negative ORs, if I said that right. Does that make sense? So that makes sense now? So that's the biggest thing right here. Somebody's going to call this right here at NOR gate, somebody in this class, especially the 3 people that are absent. And Jackson been absent 6 times. How many times has the class been? Who's Jackson? Whose partner is Jackson? Is your Jackson? Michael's not here too. But Michael's been absent a lot too. Guys, I can't do anything there. Bubble pushing. Pushing bubble.